Hi everyone, my name is Stan. As Xenex said, I'm a Customer Solutions Team Lead at GridGain, and today I want to talk to you about performance and fault tolerance of Apache Ignite's network. And first of all, for those of you who are not familiar with Apache Ignite, it is an in-memory database and distributed in-memory database with a lot of functions which are all illustrated here. It has a key value API, it has SQL, a lot of different interfaces for your application to use. It has its own disk level storage, so it can be in memory and it can be a persistent store, or it can use a third-party persistent such as an RDBMS to serve the data from an RDBMS with in-memory speed. And GridGain is set of additional components which work on top of Apache Ignite and provide enterprise-grade features such as enterprise-grade security, data center replication, and snapshots and recovery. Now let's talk a bit about what do we expect from a distributed system such as Ignite in general. What do we expect from its network? So first of all, we expect performance. When we talk about data processing system, we are always talking about performance. And for a distributed system, it means that we are transferring data fast. We're transferring user data fast. Second of all, when we have a distributed system, we need to make our bunch of separate nodes. We need to make them into a single cluster. We need to maintain them as a single system. And for that, we need some components that are normally called cluster discovery components or cluster discovery systems, which allow your machines to join into a single cluster. And we need the server nodes, the nodes which are going to store the data to connect to each other easily, and we need applications to be able to easily connect to the cluster to store and read the data. And last but not least, we need our distributed system to be highly available and fault tolerant, which means that we need to be able to detect failing nodes, and we need to be able to remove failing nodes from the cluster so that the system stays healthy, and we get our high availability from redundancy, from having a lot of nodes, and from being able to remove the unhealthy ones without impacting the overall system performance. And let's talk about these functions, and let's talk about how Apache Ignite achieves each of them. So first, let's talk about how Apache Ignite transfers business data, how it transfers user data inside the cluster, and how it makes it performant. So first, let's talk about transferring data in general. So what does it mean for a distributed system? So of course, transferring data is the key component, the core pillar of our distributed clusters, and it defines the performance of our system. And always all of the networking traffic that we have is the actual data, not system messages, not some signaling stuff. It's the user data. It takes almost all of our network capacity, because that's why we have our distributed cluster in the first place. So the key for transferring the data is, of course, the speed. And when talking speed, we mean at the same time the latency of the data transfer and the throughput. So when talking about Apache Ignite and how it transfers user data, we main Apache Ignite's component, which is called communication. So communication is Apache Ignite subsystem, which is used just for that. Almost all user operations use communication subsystem to transfer data between nodes. Data modification, SQL queries, distributed computing, service grid, all of that uses communication to send data and data requests between the nodes. Internally, communication is based on a library called Java Nio. So Java Nio, for those of you who don't know, is part of the Java Standard Edition libraries, which is responsible for fast non-blocking input-output, in particular for network I/O. And it allows the Apache Ignite to implement this optimized, fast, multi-threaded parallel I/O. And next, Apache Ignite's communication uses peer-to-peer connections. So each node talks to every other node, can talk to every other node. It means that all data accesses can be done in a single hop, which ensures minimal latency and maximum overall speed. But at the same time, we need to remember that we need to budget our connections. Connections are precious resource in a distributed system or in any computer system, and we need to make sure that the total number of open connections is somehow limited. So let's talk about the network topology for Apache Ignite. As we've already said, the communication forms a fully connected topology. All communications are peer-to-peer, and every node can talk to every other node. But considering that we also need to budget connections, we can say that idle applications should not use our system resources, should not use our connections. So Apache Ignite makes sure that when an application is idle, it will not use our connections, our TCP sockets, and the system will stay performant and will stay live. So this is the communication. This is how Apache Ignite handles data transfer, and it all sounds pretty simple, and logically it's pretty much is. But underneath it is a very complex, very advanced component which makes Apache Ignite as performant as it is. Next, let's talk about our second function, and let's talk about how Apache Ignite handles cluster discovery. And we will see that communication is not the only component that we need for networking, and that there are other functions that need different approach. So what does a node need to do to connect to a cluster? And the answer is pretty logical. So it needs to find a cluster, which translates to need to find the IP addresses the node needs to connect to. Then there needs to be a handshake between the joining node and the cluster. And finally, the node needs to exchange information between itself and the cluster it just connected to. It needs to exchange the network addresses first of all, but also a lot of other internal system information. And in Apache Ignite, there is a component that's called just like that, discovery. And discovery is the component that is used to first of all, and we will get to that, deliver cluster-wide events and deliver system events and many other functions. And first of all, it allows our nodes to find each other and to join the cluster. Then it helps our failure detection and fault tolerance. And then, as I've said, it handles the internal communication, meaning not delivery of the user messages, but delivery of the system messages which are required for Apache Ignite operations. And in turn, discovery has different subcomponents of its own, and discovery component has a subcomponent called IP Finder. And IP Finder is what's responsible for cluster discovery in Apache Ignite. So IP Finder is something that knows where it needs to look for a cluster to connect to. It provides a list of IP addresses to the node which it needs to try to connect to, and it has a number of different implementations which you can from which you can choose based on your exact system, based on your exact network topology, environment, and target environment. So the most common one is a static IP Finder, which is just a hard-coded list of IP addresses, which is great for bare metal when you know all of your IP addresses in advance. So you just list all of them in your cluster configurations. There is also a multicast based approach which allows to find all of the nodes running Ignite which are in the same subnetwork. Next, there is a shared file which is rarely used but sometimes useful implementation which stores all of the IP addresses in the same shared file, which can be updated as the cluster grows. And finally, then these implementations, they get more and more used today, are implementations based on Kubernetes and various cloud-specific tools such as AWS-based discovery or Google Compute Engine-based discovery. So these implementations, they use tools and mechanisms specific for these modern environments to find other running nodes, for example, to find a list of running Kubernetes pods with Apache Ignite. And let's briefly look at how a cluster join works in Apache Ignite. So a node starts. When a node starts, it asks its IP Finder for an IP address, which it will use to try to find a server and try to connect to it. Then the node sends a join request to the cluster, And if the cluster is actually there on that address, the node will the cluster will answer that the join is accepted, and a discovery link will be established. And after that, the node sends a special system event, which is called node join, which is distributed across the cluster, and all the nodes in the cluster now know that a new fifth, in this case, node has just joined. And we will look later at how exactly does this propagation of the system level messages, how exactly does it work. So the key points for how cluster join works. So, and when a new node needs to join a cluster, it uses an IP finder to find one of the servers that is already running in the cluster and establishes a special discovery connection to it. And this discovery connection is not the same as the communication connection, which we already looked at before. Then the special discovery link is used to exchange system level messages between the new node and the cluster. And that information includes the addresses which will be used for communication and which will be used to send the the messages with actual user data later. And after that, after all of this is done, we can finally use the information that we now got to establish the communication links to do some actual work. And next, let's talk about our last function that we defined at the start, the failure detection. And let's talk about how failure detection works on the network level in Apache Ignite. And first, let's just talk about what failure detection means for a distributed cluster. First of all, it defines high availability of our system. Our system is only as available, as fault tolerant as good our failure detection mechanisms are. But we also need to understand what the failure means in our system. So when a node doesn't do anything, it does not necessarily fail. So an idle node is not the same as a failed node. And we can also say that in a distributed system, the failure probably has something to do with network reachability. So if we can reach a node, if we can talk to it, then it's probably healthy. And if we can't talk to a node, whether it's because of a network problem or the node has crashed or the node hasn't even started yet, then the node is not healthy for us and we don't want it to in our cluster. And also we need to make sure that we are detecting the failures all the time. Even an idle cluster must stay healthy. So if our cluster doesn't do anything, say you had an end of business, your system is not doing anything at night, and then at the start of business, your user requests come and turns out that some of your nodes are actually unhealthy, they are frozen, or they have failed. Now your first requests of the day actually get rejected because your cluster is in an unhealthy state. So we don't want that. We need to make sure that even a cluster that doesn't do anything at the moment stays healthy and removes unhealthy nodes from the system. And let's try to think about what are the kind of failures, and in particular of single node failures, that we can detect. Obviously, if the entire system fails, say if the entire data center fails, nothing will help us. But if a single node fails in a distributed system, the cluster needs to understand it, it needs to detect the failure, it needs to remove the failed node from the cluster. And what are the kinds of failures that we may need to react to? So first of all, it's the lack of resources on one of the nodes, the situations such as out of memory, out of disk space, out of file descriptors, situations like that. Then a very common one is a lost connection network issue. Then, and this is very common, especially in Java world, is system freeze, such as long GC pause. The node may not even fail entirely, but if a node is in a GC pause for tens of seconds, maybe even for minutes, then we don't want it in our cluster either, because it will slow the entire cluster down. So we need to detect that, and we need to remove the node. And then there are software failures and hardware failures, which normally lead in a process crash or in a machine crash, so that from outside it will look relatively the same, just the node isn't there anymore. And in Apache Ignite, when we talk about failure detection, the discovery component is again the one that will help us to implement this function. And we talked about having discovery links, which we establish when the node joins the cluster, and these links are needed exactly for this. They needed for failure detection in an Apache Ignite system. So discovery defines whether a node is healthy and whether it's online, whether it needs to be removed. Basically, we say that there are two rules. First, if a node is unreachable via discovery, if we can't use our discovery link to send a message to the node, then we consider the node as failed. If we haven't heard from a node from the discovery link for some seconds, which is configurable, then the node has failed. And to ensure that our second property, all nodes constantly send special heartbeat messages via discovery. And this way we ensure that even on an idle cluster, there is always some minor network traffic, which is using the discovery subsystem, the discovery links, and which makes sure that all nodes are running, all nodes are healthy, and all nodes can reach each other. And this is how failure detection works in Apache Ignite. And let's look at a couple of examples of how exactly nodes can detect failures in a cluster. So Typically, we will see one of the two options. The first option is, say we have a cluster of 4 nodes and they're connected in the ring, and we will talk about the ring later, and and why it is a ring and not any other topology. And say the node number 2 tries to send a message to node number 3 with that discovery link. So when the node tries to send the message, it will try for some time, but after that, it will understand that it can't send the message to the node number 3. And at that point, using our first rule from the previous slide, unreachable via discovery means failure, the node number 2 will decide to remove node number 3 from the cluster. And the node number 3, the unhealthy node, it will be removed. In the second example, the node number 2 can send a message to node number 3, but for some reason, node number 3 does not talk to node 0, and say this is because node number 3 has an issue. So maybe node number 3 has some software error which does not allow it to continue the operation, which does not allow it to send a message to node number 0. And here our second rule comes into play. And node number 0, it sees that it hasn't got a message from node number 3 for a long time. It hasn't heard from node number 3, and it initiates some failure detection protocol in the cluster, and eventually the cluster realizes that the node number 3 is the one that causes the failure and removes the node from the cluster. And this is how failure detection works. And lastly, let's look at how system messages are being delivered. So when we talked about discovery, we talked about special discovery links, and we talked about that discovery forms this ring topology, and that sending system messages and ensuring the cluster stability is somehow different from just sending the user data. And now let's look at why is that so, and how sending system messages is different in Apache Ignite from sending user data. So there is a common theme in distributed systems, which you can see in different distributed protocols, that distributed protocols will require some mechanism for cluster-wide events delivery. Basically, what it means is that distributed protocols described in computer science in white papers, they often rely on having some base, some way of telling the entire cluster that something has just happened on one of the nodes, and by this, the state of the distributed state of the system is maintained. And this mechanism, it does not need high throughput. There is not a lot of system level traffic. There is not a lot of these internal messages. Most of the traffic, as we have said already, most of the traffic in the system is user data. But what we need from these distributed protocols is ordering. And you will see that a lot of these distributed protocols require this global ordering of events. Basically, it is needed for the system to understand the state it is currently in, and so that all nodes understand the cluster state in the same way. And let's illustrate with an example. So say we have a system with 2 nodes, a distributed system, and at the same time 2 events try to happen. One node tries to create a table, and the other node tries to create a table, and the table is called the same but has different properties. In this case, both of these events, both of these operations, they can happen. They can both succeed. One of them must succeed and the other must fail. But which one wins? Which one succeeds and which one fails? In other words, which one was first, event A or event B? And to answer this, we use these our distributed protocols. And also we have already talked about system data being less in volume than the user data, but are there any other differences in how system data is transferred and how user data is transferred? So again, the first difference is the volume, but there are also other different requirements. First difference is in reliability. If we have an issue with delivering a message which contains user data, for example, if we have an issue with delivering an SQL query or a result of the SQL query, then we will have a problem, but the problem will be a single operation failure. So in terms of user application, it will mean that an SQL query will fail and the application will need to retry, or maybe it will need to show an error to the user. But if we have an issue with delivering system level messages, this is something that can cause node failures or even cluster failures. So we can see that while delivering user data needs to be reliable, delivering system data needs to be absolutely reliable. And this is an important difference. And finally, we have already said that system messages may need a special ordering guarantees and special ordering requirements, which user data does not always have. The user data, the user operations don't all have some, all need to have some specific global order, but system events, they a lot of the times they do need some global ordering, and this is another special requirement. So we see that sending system messages and sending user messages is a lot different, and this is why we use different subsystems for sending user data and sending system data. And this is why discovery handles sending system data and communication handles sending user data in Apache Ignite cluster. So we have already said that discovery handles, well, cluster discovery, and discovery handles failure detection, but underneath it all, the actual main function of discovery is delivering this cluster-wide system events. And it does that by having a much more complex structure than communication. So communication is a simple send a message from node A to node B kind of system, but discovery, it forms a complex topology with a ring in its center and with client applications connected to the nodes in the ring, And I will not talk with too many details about the topology, but the complexity of topology is required because this is what helps us to ensure the ordered processing, and this is what helps us to reliably deliver the system events. And I also mentioned that unlike communication data transferring, which is multi-threading based, system message transferring in discovery is based on single threaded processing. So everything is slower, it's single threaded, and it's this complex topology, but all of that helps us to provide the reliability and ordering guarantees that we need. And just to quickly illustrate how the message transferring works in discovery compared to normal data transferring in a peer-to-peer system such as communication. So when a message is created, it is sent across the ring to a special node called coordinator, and on that node the message is being ordered and verified, and after that, and only after that, the message is being transferred to all of the nodes in the cluster again for the actual processing. And this is how the ordering is ensured. When a coordinator receives the message, and only after that the message actually exists for the cluster. Before that, the message is not yet there. It is not registered for the cluster. But after it reaches the coordinator, the message is processed, and the event is considered to have actually happened. And why am I saying all this frankly very technical details? And what I'm trying to illustrate here is that discovery is a component that has much more complicated, even logically, much more complicated protocol for sending the system messages, which handles a small fraction, a small but probably the most important fraction of the system's traffic, which helps the ease of use in how cluster discovery works, and the fault tolerance of the Apache Ignite cluster, and which bootstraps the nodes with all of the system information that they need to operate, and with connection information which they eventually use in the communication subsystem, which is used to do the actual work. So to again compare our two networking subsystems, discovery and communication. Discovery is used for delivering cluster-wide events, which is later on used to allow the cluster to join together and to detect node failures in the cluster. And communication is a component that is used for a single purpose for the data transfer. And while discovery is slower but more reliable with all these additional properties, communication is a simpler protocol which uses discovery as a base for its operation. And to summarize, so Transferring data, as we talked about today, transferring user data requires, first of all, speed, but operations and fault tolerance of distributed systems needs special properties of the protocol, such as ordered event delivery. It needs special protocols for cluster join and for failure detection. And if we were to implement all that with if we try to implement all that in a single protocol, it wouldn't necessarily work. But we don't have to choose between speed and reliability in Apache Ignite. Instead, we use two components to ensure both. Communication is used for fast data transfer, and discovery handles all the rest, all the internal stuff to make sure that communication can do the work that is actually valuable for our businesses. And this is all I had for you today. And now I'm ready to take some questions, if any.
Yes, thank you, Stan. We have several questions, and please add more if you have. Let me see. First question. What kind of network latencies should be expected in different high availability models with Ignite? For example, between multi-instance versus multi-zone versus multi-region.
Well, it depends on the it depends on the properties that you need in your cluster, on the kind of latency that you need from your business operations. Normally, I would say that most of the clusters I've seen are working with millisecond latencies, but here is the actual, I think that's the beauty of this separating these two protocols. So say you have a multi data center or even multi region setup. Multi-region, I wouldn't say that having like hundreds of milliseconds latency would work. This is probably a bad idea, but if you're running in say different availability zones in AWS, this is perfectly fine. In say US West 1, US West 2, this is perfectly all right. And to make sure that your cluster stays connected, that it stays stable, all you need to do is make sure that your discovery connections are stable, and you can tune some of the timeouts in the system just so that the nodes can send the heartbeats to each other reliably. And if they can do it in, if they can transfer not even a large message, say once a second, this is, or a few times a second, it's perfectly fine. And then when we are talking about actual business operations, you can structure your cluster and you can structure your nodes so that your applications only use local servers, only need local servers. This requires some work. This requires some customization or customization of the code. So this is an advanced architecture, but it's possible to make it so that, say, your applications in one region only access the nodes, the data in the same region, and in this case, your business latencies will mostly be impacted by the region local latencies, and your cross-region latency 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 will only impact the overall cluster stability, which is again handled by a different network component. So it can be so you can tune for different latencies. So say if you have local latencies on the scale of microseconds and cross-regional latencies on the scale of tens of milliseconds, I guess even hundreds milliseconds in some cases, then you can tune and build your system such that it will work and application latency will be reasonable.
Okay, thank you, Stan.